Yeah, it's easier if they don't show up in that tiny window in the door.
Yeah, it's a bad room for that.
I was more thinking if they didn't need the videos in a different way than usual.
As well.
So that's why I was too spidey because they were.
They didn't say they were coming. They did not say they were coming. I was James Barry and said, it's one where the pro meetings in Leipzig.
Come here, new camera to introduce you. So welcome all. Nick Pham has come to give a talk to us today in person, so this is a privilege. Thank you very much. Nick is a lecturer in the University of Cardiff, where he leads the Agile Cyber Physical Systems Lab. He has earned his PhD from Oxford, the computer science department there, and he has collaborated in a startup leading with Earable and One Computing. And so thank you very much, and we look forward to listening to your talk.
Yeah, thank you very much for the invitation, Cecilia, and also for everyone in the team for accommodating me today. Also, thank you everyone watching over Zoom as well. So it's Nick. So usually I go with that name, so feel free to call me that. So today I will talk about my research visions about enabling efficient and intelligent embedded system for the next generation of human healthcare and well-being. So Abhishek will not only cover the thing that we have done, but also I will also go through the thing that we are doing and the plan for the future as well. At least from my personal visions for this area. So a little bit about myself. So as you can see, I finished my PhD back in Oxford. So my PhD was fortunate to be funded by Oxford University scholarship. And also before that, I actually initially started my PhD in America. Then I moved in the middle of my PhD. And then, even before that, I have my master's degree by research in KAIST in South Korea. So these are just a little bit about highlight about my career. So I do have quite a few kind of publications in highly selected venues. For example, MobiSys, MobiCom, Sensis. Probably many of you will already know. Also, I recognize as the future research leader of the Southwest and Wales area of the UK. Also, a few dissertation award nominations, and also some of the research highlight as well. I'm currently leading my own team with several funded projects from different kind of funder, including EBRC, Alan Turing Institute, the Academy of Medical Science, etc., etc. Okay, so one of the things that actually I feel very enjoy in this academic career is the people that I work with. So these are the team that I'm having in Cardiff. So I have 2 PhD students, also a few research assistant and postdoc, and also research intern. I also affiliate with the EBRC Center for Doctoral Training at Oxford University, where I have been teaching for the first year PhD student. And actually one of my first student to graduate recently, and I was from that CDT, from that center. So this is a lab that I'm having in Cardiff in the last year that we build everything from the ground up. So we have biosensing, a station for rapid prototyping, electronic testing, the hardware development. So probably if you look at the lab, you probably know what I'm doing. exactly. Basically, like both hardware and software at the same time in the whole kind of system integration point of view. So just a few quick like keyword about what I'm doing. So if you want to take away a little bit about like our talk today, so these are the 3 keywords that I want everyone to basically remember about me. So the first thing is human-based biosensing. I do quite a lot of stuff on like enabling a different kind of like sensing modality for like from the human body. I also do a lot with like wearable, and I also do some of the like on-chip intelligent development as well. So the motivation for these everything that I'm doing is basically, if you look around, there are like billions of like embedded like computer like around us. There's a lot of like IoT device, we have wearable device, we have implantable device, etc. However, if you look down to these like computer, they face the same problem. That is, it is not as smart as they should be. And many of that actually because of the constraint of the energy that is can able to like get like power, like, and then so these energy and computational resource constraint, we basically push these kind of computer.
I'm gonna press that. Can you see that? I guess you don't have that view.
I don't have that on me
Okay, yeah, that's
for some reasons.
Because it's the record. Oh, yeah.
Yeah.
Okay, great. Thank
Yep.
you.
Okay, so because of the constraint in terms of energy and computational resources, all of these kind of like embedded computer have to rely heavily on offload device. That is something that you can easily see with the like smartwatch that we are wearing like nowadays. It's basically require a smartphone like in tandem together with a smartwatch in able to run something meaningful. And for some like healthcare application, that turnout can be fatal. However, if we look at inside our human body, we can see that our human brain is actually one of the most efficient computer in the world, right? Because it has like trillions of neurons, but the amount of energy that it consumes is less than the energy that actually from the liver, right? So in my visions, I was thinking that in the very near futures, we will have like hundreds of like embedded devices that invisibly attach to our human body. And all of those devices, like when it's like attached to our body, basically can monitor and also even modulate our biological processes and signal. And if we can do that, then it can enable a lot of like healthcare and also like well-being applications. So the question that I have been putting, the hypothesis, like the fundamental hypothesis of everything that I'm doing, is can we learn from our human brain to design like a smarter and more efficient embedded computer in order to improve our healthcare and well-being? So these are the 4 main research directions that I'm working on. So the first thing, like very similar to what the brain, if you look at the brain, in order for the brain to work, basically it requires information, right? So for our human body, basically we have like 5 senses, like the eye, the ears, the mouth, the nose, etc. So basically these like provide information for the brain to basically react on something. So that's one direction. So basically we need to enable a more novel sensing method to basically provide the information that required for the computer to operate. And after we have that information, how can we enable like very kind of efficient like embedded intelligence that can be deployable on the device? And so if we look at the brain, it doesn't have battery, right? So actually our human body is already a mobile battery pack. So what is the brain is like power with sandwiches, maybe noodle, maybe rice, right? So actually quite efficient in that way. So when we think about the wearable device, so now we only have one device, so that one battery is okay. But if we have like 100 devices, how can we charge like 100 devices every day? So energy is still a big barrier that prevent those kind of like enabling technology to become like viable. And if we can solve on the problem, I believe that there's a lot of application that we can do. Okay, so the first question is like, how can we enable like a novel sensing modality? So these are actually the things that like I have been doing in the past few years. So one of the first project that we started quite some time ago, and probably many of the audience already know about this, is about the wearable, the earable device that can capture a lot of signal from our brain. So actually, the location of the ear is quite, I would say, the fairly good locations in a way that it's close to a very important organs on our body. So it's very close to the brain with the central nervous system. It also close to our eyes, it close to our muscle, facial muscle, and also a lot of blood vessel and also the sweat gland as well. So for this project, we try to detect microsleep, because when you're driving is one application, working in the factory is another application where there's a time that you become very tired and you can pass out for a few seconds. And those few seconds can be fatal. Imagine if you're traveling on the highway with about 60, 70 miles per hour, 5 seconds, it means that life and death situations. So how can we detect this? So the idea is yes, the earable device can capture all of these biomarkers that link to microsleep. So, but how can we design that in a way that is very compact? It can be low cost and it can be used daily. And also it needs to be socially acceptable in the mean that basically people can feel comfortable to wear it every day. So these are the main challenges that we face. Yes, the first one is basically noise and motion from the environment. Why is that? Why we did not have that before? EEG system actually only available in the hospital. But actually, when we put that EEG system outside the hospital, outside the lab, it basically doesn't work. Because there's a lot, when you move, there's a lot of activity that create motion artifact. Also, inside the hospital, if you have been in that kind of EEG room, basically it gets shielded from the environment. So basically, at the light that we are turning on have noise as well. So everything that we are using, all of the electrical devices that we are using have noises as well. And we have that in the real environment, but not thing that people consider usually in the hospital or in the lab. So that is the first and the main challenge that we have to address. The second thing, if you look at the EEG device in the hospital, they have a lot of sensor on our head, which basically, well, very obvious, it's not socially acceptable. So how can we make that to become well, it's more compact, it's more easy to wear. And when we put something behind the ear, the location is actually people haven't at the time that we're doing this, people haven't explored that before. So it's quite challenging in a way that we don't know what are we going to get. And when we try to do some preliminary study, we can find out that the signal actually very weak and it's overlapped in terms of both amplitude and also frequency. So in order to solve the problem, so we basically have a few things that we did. One is we identify a minimal location behind the ear. Actually, this one, we only need to 2 sensing point behind the ear that basically we can capture all of that biomarker for sleep. Basically, we are talking about brain activity, eye movement, muscle contraction, and sweat gland activity. And then we design real-time motions and noise mitigations, which basically work directly on the hardware. So this is hardware level. So you see here, so this is working without our hardware, and this with our hardware. You see the signal is fluctuate significantly with our hardware, but without our hardware, and with our hardware, basically all of that gets suppressed, and it's work in real time, and it doesn't require basically you to do the training every time as well, because basically it's fix the problem at the hardware level, and we basically do the evaluations on about 90 subjects who basically deprived from sleep, and also some narcoleptic patient as well. So we have the video EEG system from the hospital at the ground truth, and also we have the doctor who do the labeling for us as well. So the result is quite encouraging, where we test that on the people that we don't know, and we have about 76% of precision and also 85% on recall for the people that we haven't seen on the data set. So this is quick demo about the device that we built, the prototype that we built before.
alertness. As the user becomes drowsy, their alpha band power increases. Earbol automatically
So
dims
he's
the
wearing the
lights
device
and plays
and
relaxing
basically
music,
try
reducing
to
the
sleep.
latency to sleep.
And the idea is like we try
Accurate
to
sleep
improve
staging
the sleep.
continues throughout the night until the user becomes alert when their alpha band power decreases. Earbol then automatically brightens the lights and plays music to wake up, reducing time to wakefulness. Earbol detects an open mouth, signaling the drone to rise. When the user grinds their teeth, the drone moves forward. Looking to the left causes the drone to turn left. And likewise, when they look right, the drone will turn right. This technology includes a suite of hands-free human-computer interaction, enabling new abilities to control the world around us.
Yes, that is a very quick demo to show that actually this technology actually work. Okay, so another paper that probably many of the people here already know about is the one that we do for the blood pressure. So one of the things that we like the motivation for this one is that if you look at the people with hypertensions, basically they have to wear the device, the cup-based like blood pressure monitoring device, basically every day, in order to like do the monitoring, which is not like convenient, it's quite inobtrusive. So what we want to build is like a system that basically they can wear like an earphone, and we can do the same thing. So one thing that we find out that if we go inside the ear, there's an artery in there, and basically we can capture the blood pressure from there. So basically the idea is like the fundamental idea is very kind of simple, that we press on the artery and then we measure the reflection in terms of the pressure. It's not that like trivial as it seems. So two main challenges that we face is basically in order for the cup-based device to work, basically it need to block the artery completely in order to like capture like both like blood pressure. And we cannot do that inside the ear because we can only press on one side, but we cannot control the other side. So that is one challenge. Another challenge is like the ear canal is very, very small. So how can we design a sensor that can go in there, press on the artery, measure the blood pressure back, and then get the result? The way that we solve this problem is the first one start with the hardware. Okay, so basically we need to have something that able to go inside the ear and basically able to somehow press on one side. So we come up with the idea of the balloons. So we basically use a medical balloons. So you probably can find that what it actually is used for. But yeah, so it's a medical balloon, it's a silicon base, so it's quite robust in a way that it will not burst that easily. And it's designed to basically go inside the human body. So basically we know that it will be safe when we put something in there. But the balloon basically, when it's inflated, it's basically inflated in all directions. So basically it doesn't work if we have a sensor that placed on top, because when you inflate it, it basically creates a pressure on the sensor, and the sensor will basically bounce off. And even if the sensor can stay, you cannot get a good measurement as well, because now the sensor doesn't basically work in a way that it's supposed to work. So the way to solve this one is basically we have an idea that how about if we can only inflate in the one directions and keep the other direction stable. And the way that we do it is actually we have some silicon, and then we cure the silicon at high temperatures so that it harden the silicon. The silicon basically makes some arc reaction with the balloon also is silicon, and also it's hardened on one side. So that side stays stable, and it's only inflate on the other side. We also put some others like a soft silicon layer on top. So that is basically creates kind of like a soft kind of like barrier when it's inflated to the ear. And we also came up with so we find out from researchers, there's a way that we can measure the blood pressure, estimate the blood pressure without blocking the artery completely. So we can only like push the pressure to a certain limit, and then we can calculate the other point without blocking completely the artery. We test this prototype on about 35 subjects, and we have the errors like within the limit for the standard limit for the blood pressure monitoring device. Okay, so these basically what we have done about like how to enable the different kind of like sensing modality. The next question is like how can we enable, so when we have all of that information already, how can we efficiently process the capture the biosignal? So these are the things that we have done before. Probably you know already. So basically these are the work that we collaborate with the team. And so one thing that we find out that many healthcare like biosignal based applications are not very practical for wearable devices. There's a few fundamental challenges for that. One is that usually for healthcare application, it requires very long-term like monitoring with high fidelity signal. So we are talking about weeks or days, not just about a few hours. And that basically will turn out to be quite a lot of data rate in terms of the telecommunication protocol in order to send that to the phone or something like that to process. And some of the applications require low latency response. So for example, if we're talking about epilepsy, like seizure detections. So like a few seconds late can mean like life and death for the patients. And we put on the constraint on the wearable device, which usually have very small battery and very resource constrained devices. Basically, it's not that easy to achieve with all of these. So the solution that we came up with is, for example, so for this one, we're talking about seizure applications. So we can collect, there's a lot of data that we collect over time, but usually seizure only happen in a very small amount of data that actually show. But we have to constantly monitor those data because it can happen at any time, and we don't know when it will happen. One thing that we find out from the signal is that these kind of seizure activity have a certain pattern. And then we can break that down from the medical knowledge that these are some of the patterns that usually will happen with usually will go with seizure. For example, a spine wave kind of pattern on the EEG, the absent seizure have about these kind of waveform, and tonic-clonic seizure we have that kind of waveform. And then basically based on that, we can devise a kind of a very tiny pattern recognition model that can be deployable on the device. And even so that can eliminate quite a lot of data already, like some of the data that we don't need to care about. But how can we push that even further? So we also came up with a pattern-driven and compressive sensing method so that we can use that information about the pattern that we detect and use the optimal weightless transform in order to compress the model even further. So we test these kind of system on an open data set with about 120 subjects and with 6 biosignal pattern. So we can see that these kind of small pattern recognition model can achieve very high on-chip detection rate. So we achieve about 75 to 96% in terms of sensitivity and specificity on 20 people that we don't know in the training data set. These kind of model are also very lightweight. It's about each model only about 35 kilobytes of memory. It's only run for inference time is only about 27 milliseconds on 120 microcontrollers. So we put these on a new seizure application, a seizure detection use case. We leave out 10 people that we don't know from the data set, and we can see that now we can detect seizure with about 85% of sensitivity. In the meantime, we can reduce the amount of data that we need to transmit out about more than 24 per time while maintain the same high fidelity that required for clinical applications. And that will translate that the improvement of more than 1000% in terms of energy efficiency. And with that, now the device, instead of running for a few hours, now we can run for the whole week while continuously monitoring for seizure pattern. Okay, so the third direction is how can we power all of these sensing and computing modalities. So these are the things that we actually working on at the moment. So we get the funding from EBSRC for the next 4 years for a PhD project to basically work on this. So the idea is actually if we look at the human body, there's a lot of energy that we produce. For example, when we walk, we produce about 60 watt energy from our kinetic like movement. And also there's a lot of energy from the environment as well. So how can we harvest the energy from one point and transfer the energy to another point so that we can power all of these kind of like applications? Because we can have a lot of energy like down to at our leg, but basically there's not a lot of information there. But we have a lot of information here on the head. So how can we harvest energy over there and transfer the energy like up to the head, for example, if we have a wearable device, for example. So I will go through a little bit about some of the kind of like our real world deployments and also the commercialization like effort that we have done. So this is one of the kind of study that we run in the hospital for like 2 years with our collaborators. So yes, that is the same kind of seizure kind of like applications that you have seen before. So actually all of these like we developed have been deployed in the hospital for about 2 years, and we collected about like 32 like patient with seizure. So we can see that we can have very good kind of accuracy that we have in terms of like data like detecting seizures. And this is like basically one of the startup company that I have to basically raise based on the technology that we develop. So in this case, we basically build a headband instead. And we test this one with the companies on more than 300 subjects. And we can show, and this was published in scientific report like last year. And we can show that we can improve like people sleep about on average about like 19 minutes for people to get, like, sleep faster. These are some of the things that I'm doing with my team at the moment as well. So we also have another funding to do like stress quantifications. So basically one of the preliminary studies that we published in the workshop like recently is to basically use foundation model and with the biosignal that we are collecting with the device in order to detect like whether people feel stressed or not. Also, I'm working with like the people in the University Hospital of Welsh and also a special kind of like learning school in Welsh in order to use the technology, basically to try to like detect like sensory overload from autism children. So these are still the ongoing work. So stay tuned for some of the updates. So these are basically the quick videos about the device that we built from the company.
Sleep is vital for good health, but many of us are struggling. Experts recommend adults under 65 get between 7 and 9 hours of sleep per night. But according to the Centers for Disease Control and Prevention in the US, 35% of us report sleeping for less than 7 hours per night on average. At least I know I'm not alone. I've tried using podcasts, white noise, pretty much everything, and nothing's really worked. Now, this is the Friends Brain Band from Earable Neuroscience, and they claim that it can use a variety of sensors to measure 7 different metrics, including brain waves and your facial movements as you sleep. The headband has bone conduction headphones, which sit just above your ears. They play audio content in response to its sensor readings in real time, including meditations, nature sounds, and music. The inbuilt AI then learns how your brain responds to different types of sounds to try and figure out what's most likely to help you drift off. So I'm just looking at the graphs here on the screen, and it's showing me 3 different things, one of which is the EEG, which is my brain signal. That's pretty flat at the moment, which is, pretty on brand. And then underneath that, we've got eye motion, which is slightly strange. It looks like it's detecting when I move my eyes around, and it's reacting on the graph. So that's pretty funky. And then at the bottom, it's facial muscles. And if I kind of open and close my mouth like that, it also reflects on the graph here. So it's pretty impressive that it's detecting all of that just from something that's basically wrapped around my forehead.
Yes, so that's basically everything from me. So yes, so thank you everyone for being here today. So happy to take any questions.
Thank you. If you're online and you want